Okay, so welcome to acid lesson number 2. Please turn to page 37 in your notes package. We'll do a couple of the review questions of the U-tries before we move on to the next concept. Our first U-try is KOH. So it says, write a chemical reaction or a chemical equation to show how the following bases would dissociate in water according to the modified Arrhenius theory. And then it says, name each base. Okay, so we need to, okay, so we had to determine, well, first off, I'm going to start with, is this an acid or a base? I know it does say that it's a base, but it's always important to know which ones are acid and which ones are bases. So according to Arrhenius, bases are ones definitely that contain a hydroxide ion in them. So that being said, you do see your hydroxide ion here, so you know that it is a base. So we do have a base. So what we're going to do is we are going to write down our KOH. Here it says it's aqueous, and that's only because it's dissolved in water, but technically it starts out as a solid being thrown into water. Now, KOH, we're going to learn more about today because we're going to learn about strong versus weak acids and bases. So this means that it is going to dissociate completely into a hydroxide ion and a cation. So I know that my hydroxide ion is OH minus, and it's going to be aqueous, so we put AQ at the end. So what's left in my KOH is obviously the K, so then I put my K here, put aqueous. Now I need to determine what its charge is. You can either use the data booklet, okay, or you can use the fact that we have a 0 charge on the reactant side, and we need to make a 0 charge on the product side. So right now I have an overall -1, so you'd have to be a positive in order to balance it out to a 0 charge. Okay, so our charges are balanced out. I have 1K, 1O, 1H, and then on the reactant side, I also have 1K, 1O, and 1H. Our next one is CaOH2. It says pretend this one is soluble, and I'll mention this more in detail when we do our strong acid and bases. Okay, so we have CaOH2. Now I wanted this one in here because it's important for balancing, because they're not always as straightforward as in A. So I know that this one is a base, definitely because it has that OH in it. So rewrite your CaOH2, and technically a solid. So this one is Ca stands for calcium, so this one is calcium hydroxide. Our top one was K, so that's potassium hydroxide. According to Arrhenius, we have a hydroxide ion, so OH minus, aqueous, and then you ask yourself, what's left over? So what's left over is Ca. Now, the charge, again, hydroxide is a -1. We have no choice in the matter. It has to be a -1. Over here, it says that I have 2 hydroxides, but on this side, I only have 1. So I need to put a 2 at the beginning to balance out the fact that I have 2 hydroxides on my reactant side. That makes this overall charge on this side right now a -2. So if I have a 0 charge over here on my reactant side, this must be a +2 charge in order to balance out to a 0 charge aqueous. Okay, there's my first 2. Now I'm going to scroll down because I'm going to need a bit more room for this next one. So I have NaCN. So this one is an ionic compound. And according to ionic compounds, you have to determine if it's soluble versus insoluble. So rather than me flipping back and forth, I'm just going to tell you that this one is soluble because it has Na in it, and cyanide. So this one is sodium cyanide. So the first step in these ones, when you have an ionic compound, is you have to do your dissociation equation. So NaCN, we have a solid. So what does it dissociate into? Well, we have our Na ion plus our cyanide, which is Cn. Cyanide is a negative charge. Sodium is a positive charge. And we have aqueous. Aqueous. Second step, and that is balance, because 1 Na, 1 Na, 1 C, 1 C, 1 N, 1 N, zero charge on both sides. So step 2, whenever you have your ionic compound dissociating, and you look at your products, you have Na positive and Cn minus. If you don't have in your negative charge or your N ion and H at the beginning, then it has to be acting like an acid. Or sorry, it has to be acting like a base. If it had the H at the beginning, it'd be acting as an acid. Okay, so then that means that what we're going to do is we're going to take that Cn minus and we're going to react it in the presence of water, which is H2O. So liquid. This is already aqueous because it's dissociated in water. Okay, now according to the modified definition of Arrhenius, is that the anions are going to react with water, okay, to make a hydroxide ion. So look at your reactants. The only place that you have your O and your H is in the water molecule. So that means that the water molecule has to do something to become OH minus. So we have OH minus has to be aqueous plus. Okay, well, that extra H, we lost an H. Okay, that has to go somewhere. The only other place it can go is that cyanide ion. So it has to go to the Cn minus. So now what we're going to do, and we always attach H's back to the beginning. So now we have HCN. Remember to do capital letters for all of these. So cyanide was a -1. You just added in, so your bank account was at a -1. You just put and added to that bank account a positive charge, and just one positive charge. So going from a -1 to adding an extra $1, your bank account is now at 0. So that is why I did not put a charge on your hydrogen cyanide here. So this is now aqueous. Okay, letter D. So we have K2CO3. So I see an ionic compound. First step, I have to dissociate. So step 1, K2CO3, solid. So I have to dissociate. My two ions that I see in there are CO3 and K. So I'm going to put K plus CO3. Now, charges. You may be able to tell what the charges are based on everything you've done so far. But if you don't know the charges, then you get out your data booklet. So my data booklet, you find one of your ions up here because K2CO3, you have 3 atoms. That means that you have to have at least one polyatomic. Okay, so there's none that has the K at the beginning, so that means that there has to be the CO3 that's located here. So you look around, find the CO3. There it is, carbonate. So CO3 has a -2 charge. So I know now that carbonate is a -2 charge, aqueous. Potassium is a +1 charge, also aqueous. Now balance out your charges. You have a 0 charge on this side, you have a -2 here. You have a +1 here, so I need 2 of these to balance out the 0 charge. Now I have 2 potassiums on the reactant side, 1 carbon, 3 oxygen, 1 carbon, 3 oxygen. So now I'm balanced. Now I look at my products. Of my anion, is there an H? No. So therefore it's acting like a base. So step 2 would be to take your CO3 -2, aqueous, and reacted in the presence of water. We're still making a hydroxide ion. So I know OH minus, OH minus. So I need to erase that. And then I'm going to add my AQ to the end. Plus, and then look at what's left. Since this water molecule is losing hydrogen, you have OH left. That H is now attached to whatever the carbonate is. So now I have HCO3. Now your bank account. Your bank account was at a -2. You're adding in one hydrogen ion, or technically a proton, either way you want to use define that as. But what that now means is you're adding in one extra positive. You have a -2, so that brings your bank account to a -1. So we have now aqueous. Now I still have a negative charge here. So this ties in acid, so we're going to leave it here for now, and we're going to move to our acid examples. So we're going to scroll down. So now it says write a chemical equation to show how the following acids would react with water according to the modified Arrhenius theory. So name each acid. And so our first one is HBr. So acids are, students always tell me acids are easier to do. For some reason, acids donate, so they are a lot easier to understand. So this one, HBr, so we've got to practice naming our acids anyway. So this one I would name like ionic compound. So this would be hydrogen bromide. So that looks like rule 1 because it's "ide." So then, and again, you can go back to your data booklet to figure that out. But "ide" changes to "ic acid. So I'm going to have "ic acid." And then the hydrogen becomes hydro. So I'm going to put hydro. And then I keep that brome. So hydrobromic acid. So HBr is hydrobromic acid. Okay, so when we have an acid, I know this is an acid because it's an H at the beginning, AQ at the end. They react with water, H2O. Acids donate. So when acids donate, they donate a hydrogen ion. So if you look at your acid, your HBr, if it donates one hydrogen, what's left is a Br. So your bank account was at a 0. If it loses one positive charge, that makes it a -1. So now we have aqueous plus. The hydrogen has to go somewhere, and according to Arrhenius's definition, his modified definition, is that water is going to accept that hydrogen ion to become a hydronium ion. So now we have H3O plus aqueous. Okay, there's one example. Okay, let's go to B. So we have, oh, here's a tough one. So we have hydrogen. Now I don't even know this one off. I think this one's chlorate, but I'm going to double check because ClO4. Okay, ClO4 right here. Oh, it's perchlorate. Ooh, tough one. So I'm going to put hydrogen perchlorate. So according to my acid rules, this is not like number 1 up top because I don't have an IDE. So this has to be rule 2. So in rule 2, you get rid of hydrogen and then you change 8 to ic acid. So this one is perchloric acid. Okay, so HClO4 aqueous plus H2O liquid. Acids donate. So then ClO4 lost a positive charge. So now I'm at a -1 and we become aqueous. All acids create hydronium ions in water because they react with water. So there you go, balanced. Okay, the last one I'm going to do, I'm going to skip HNO3 because that one's pretty easy. I'm going to do D. So D is a little bit of a tricky one. And we have H3PO4. So this one is phosphoric acid. You can try and come up with that before, or pause the video, go back and figure out how you got to that one. So I'm going to start with the H3PO4 aqueous. Going to react with water, which is H2O, liquid. Acids donate. They only donate one hydrogen ion at a time. So H3PO4 would become H2PO4. It lost one positive charge, so now we're at a -1. Plus H3O plus, your hydronium ion. Now, the trick about these ones is you go until you no longer have hydrogen ions existing within technically your original compound, because this came from your original compound. Okay, so this would have been step 1. So step 2, now I'm going to take that H2PO4 minus 1, and I'm going to react it with another water molecule because you're throwing it in water, which has more than one water molecule. Okay, acids donate. This H2PO4 minus 1 is acting as an acid. So that means I'm going to take 1 off, HPO4 minus 2 now, because you're taking away another dollar. You're spending another dollar you didn't have. Aqueous plus H3O plus and aqueous. And do I have all my hydrogens gone? No, I don't. I have one still there. So that means I have a third step. HPO4 minus 2 aqueous, reacting in the presence of water. Okay, so remember we have to make a hydronium ion. So the only way to do that is to get rid of all of my hydrogen ions from my acid forming substances or my acid substances, and I get PO4, which is your phosphate molecule, and another hydronium ion. Okay, so this now leads me to strong acids and strong bases. So I'm going to skip ahead here. Okay, strong acids and strong bases. Sorry, strong versus weak acid and bases. So in the notes package, we're going to be doing a little bit of kind of graphing, but not detailed graphing like you would do in physics. So now we're going to change the definition slightly for what acid and bases are, and we build on it every day. So our first one is talking about strong acids. So not all acids and bases are going to ionize or dissociate to the same degree. So acids ionize and bases dissociate, which is why you see it worded that way in your notes package. So you can choose to highlight if you want. So strong acids are going to ionize at nearly 100% in water. Okay, so it says use the following diagram to explain how strong acids like hydrochloric acid, use the following diagram to explain how strong acids like hydrochloric acid ionize. Okay, so if we look at this, I'm going to get my pen back here. We are saying in this example that we have hydrochloric acid. Now, hydrochloric acid is HCl. So HCl is our hydrochloric acid. It's going to react with water, H2O. Okay, we know according to our rules in the first one that acids are going to dissociate, our acids are going to donate a hydrogen ion. So then what we have left is the Cl minus, aqueous, plus H3O plus. So really what it's saying is my acid is going to break apart completely. okay, at least or all to nearly 100%. And you can see that in this example. So in this example, you can look at this molecule. So this is this molecule here, the white and the black dot, are representing HCl. So H and then Cl. You can see in the products that you don't have any more HCl there. It is showing you that it's completely separated. So that's implying that you don't have on the product side any more acid. So what we would see in a chart or a semi-graph, your HCl in your reactant side is going to be 100% existing as HCl. Your H3O plus is going to be near the bottom at around 0%. So the symbols that you're seeing here are something like this. That means about or around. Okay. And then your Cl minus is again at roughly 0%. So this is your reactants. This is your products. So how do your reactants differ from your products? So HCl, H3O plus, Cl minus. So since we're a strong acid, that means that your HCl is going to be nearly 0% over here. And what you're going to see for your H3O plus is, whoops, that's a horrible. We'll just do this, pretend I did that on purpose. We have nearly 100% dissociated or ionized, sorry, into your hydronium ions and your chloride ions. Okay, moving down to weak, or sorry, before I finish, strong. So the concentration of the hydronium ions is the same as the concentration of the acid it comes from. That is really, really important. So this will become important when we start doing calculations at the end. So I would take a highlighter and I would highlight this. So the concentration of the hydronium ions is the concentration of the acid that it comes from, as long as it is a strong acid. So it is important to understand what this means in terms of being electrolytic, or technically the properties, or what does it mean for the properties of the acids. So what does it mean for being electrolytic? So what it means is that if you have a strong electrolyte, it's going to have more available ions to conduct. Anytime you are an electrolytic substance, it means you, going back to your solubility, it means you dissociate. You have ions available to carry the charge. So if you have more ions, it means you have a higher electronegativity, a higher ability to conduct electricity. So this means more ions available. It equals stronger conductivity. Okay, now reacting with a metal. Again, we have more ions. If we have more ions, that equates to more reaction. So that means that we're going to have a stronger reaction with metals. And then the last one, again, the more ions you have available, then you have more ions available to react. So more ions equal quicker reaction rate. If you have less ions available, that means that you have a slower reaction rate. Okay, these are the only 6 strong acids that you must memorize these. Okay, so I would suggest putting this in your notes pack or in your data booklet somewhere to memorize, I would just put the formulas down, because if you see your formulas, then you know that, or you should be able to convert this to a name based on your rules for naming acids. Okay, our next one is weak acids. We're going to go down. So weak acids do not ionize completely. So that means that they're not going to separate as well as your strong acids do. So I want to highlight this. So weak acids do not ionize completely. Only a small percentage of ions will form in the solution. So what we're going to do is we're going to take a weak acid like hydrofluoric acid. So we're going to take HF, aqueous, and we're going to react it in the presence of water, so H2O. Now, normally, now this arrow is going to look funny. Okay, so this is a different arrow, and it meant equilibrium when we were talking about solutions, but here it actually means a weak acid. Okay, so maybe put weak acid. So it will still make your hydronium ions, but technically less of them. And then it will make your fluorine ions, but again, less of them. So if you look at your container as a product, you don't have all of your acid separating into the ions. You still have some hydrofluoric acid in your product, but you also have some hydrogen ions and you still have some fluorine ions. Okay, so what that means is weak acids do not readily ionize. So the concentration of the products differ than that of strong acids. So it's not going to be 100% like in the previous one. So if we were to draw reactants versus products. So this would be my reactants. So if I have my hydrofluoric acid, we would have as reactants, this is very similar to your first one. You'd have around 100% of your hydrofluoric acid, 0%, and 0% because they haven't dissociated at all. 0%. As your products, what you're going to get is, now this differs. So put your HF, H3O plus, and your F minus. So most of the ions, or most of the hydrofluoric acid, is going to stay as hydrofluoric acid because it's not going to want to dissociate. So around 99% is going to stay as hydrofluoric acid, and around, so this is going to be a little bit higher, around 1% will dissociate into its component ions, or it will ionize into its component ions, so H3O plus and F minus. So we use equilibrium arrows for weak acid equations as they react less vigorously with metals than that of strong acids, and they make weak electrolytes, so they're not going to conduct electricity as well. Weak acids will react until no more hydrogen ions are left in the original acid, but it's going to be really slow. Okay, our next one is strong bases. So strong bases are going to dissociate 100% into ions in water. So any strong base is an ionic hydroxide of groups 1 and 2 with a hydroxide. So if you have a group 1 and 2, so group 1 and 2, going back to your data booklet, is talking about these first two columns. Okay, so group 1 and group 2 combined with hydroxide will be strong acids. Okay, so our first one, we have sodium hydroxide. So sodium hydroxide is NaOH. So we write NaOH as a solid, as we always do. They are going to dissociate completely into their component ions. So we have Na positive, aqueous, plus OH minus, aqueous, balanced, done. Now, when I go to my barium hydroxide is BaOH and then 2, aqueous. Now, the reason I know that is because barium is a +2 charge. So right here. Okay, so that means I need 2 hydroxides to balance out that one barium. Now, what's important about some of these bases is that some of these strong bases, according to the solubility chart, are insoluble. So barium hydroxide, for example. Okay, hydroxide, barium would exist in most, so that means that it's low solubility. But remember when I taught you this and I talked about solubility, there is still some that will dissociate. The majority doesn't. Like the 1% that does, it's very small. So we show the majority of not dissociating. But in the case of looking at it in terms of a base, even though the solubility is low, the fraction, the like 1% that does dissolve, will dissociate at 100%. Okay, so we still show it as dissociating because that small percentage that does dissociate will dissociate at 100%. Okay, so that means I do my dissociation equation just like I would in the previous one. So I get barium. Barium has a +2 charge, aqueous, and hydroxide has a -1 charge, aqueous. This one you have to balance because you have 2 hydroxide on the reactant side. I need 2 hydroxides on the product side. So there you go. There's your strong bases. So now I got to do my weak bases. So for my weak bases, I put those on the next page. So weak bases, just like weak acids, do not dissociate at 100% into ions. Oh, I made an arrow. Look at that. So only a small percentage of the base will form ions in water. You also use equilibrium arrows to show your equation for weak bases. So since it's a weak base, then we must use equilibrium arrows and we must show it reacting with water. Okay, so that's different than the strong bases. Okay, so here I have OCl minus, so this is aqueous. I know that this is not a strong base because it's not an ionic hydroxide. So then I must react it in the presence of water, so a liquid. Okay, in this case, oh, I did the wrong arrow already. Okay, since it's a weak, sorry guys, since it's a weak base, you need to put your equilibrium arrow. So that means that we need to show the fact that we have our water molecule donating a hydrogen ion to your base. So now, I'm just going to show this arrow. You don't need to put this in your notes. One of these H's is going to go over here. So if one of the H's goes over there, then I become HOCl. Again, H's always come first. Your bank account was at a -1 here. Now you're adding a hydrogen ion, which is a positive charge. So that balances it out to a 0. So now I have aqueous plus water lost 1. So we get our hydroxide ion, which is created in all of your bases. Next one, we have Cn minus. So this is aqueous, not a strong base. So therefore add in the presence of water, liquid. Therefore it has to be weak if it's not strong. So again, acid is going to donate. So that means that we add to our Cn minus, HCN becomes aqueous. So this means that we have to take away that hydrogen ion from water to become OH minus, aqueous. So weak bases are going to react until no more negatives are left in their original anion. So we'll talk about that more in our next lesson when we talk about poly and monoprotic acids. So going down. So what would reaction rate and conductivity look like in a strong versus a weak base? So this is very similar to our strong and weak acids. Okay, so if you have a strong base, this would equate to a quick reaction and higher conductivity as we have more ions available to react. Okay, now I did create a takeaway at the bottom. Feel free to read that. And then what you need to do is you need to complete the U tries on the next page. So you see the U tries here on page 41 and 42. Oh, sorry, 42 and 43. And then tomorrow we'll talk about monoprotic and polyprotic acid and bases.